Hello, so I wanted to talk a little bit about what I'm currently working on. I just want to make more videos in general, so I thought I'd talk about stuff. And what I'm currently working on is a compression algorithm and decompression routine for level data for the NES. Now, the NES doesn't have a lot of memory it gives you in cartridge space and RAM and whatnot, so you gotta make the most out of what you've been given, and there comes a point where you start realizing that compressing level data is pretty much required. So the routine I'm using, it's a type of encoding called run length encoding. It's a very old type of compression, very well known. Here's the basic concept of it. So you give it a set of data. Um, my data consists of tile values to write to the screen. So let's just say there's a bunch of tiles that are consecutive. And those are going to be, this is going to be our data set to just theorize about what this encoding does. So it counts the number of consecutive tiles and outputs a length, basically like a counter. So I want to count these F's. So I got 1, 2, 3, 4, 5, 6, 7, 8. I would put 8 down as the counter and then F down as the tile value. You would then do the same with consecutive tiles. So 1, 2, 3, 4, 5, 6 is the counter, 0 is the tile. Over here we have 5 as our counter and 1 as our tile. So we have 8 double F's, we have 6 zeros, and we have 5 ones. I think that's pretty easy to understand. And look at all the space we saved. So this up here is our uncompressed data, and then down here is our compressed data. Now there is an issue with this method. So it worked all fine and dandy with this data up here because it had consecutive values. But what if we have unconsecutive values? Like let's say we were drawing a checkerboard pattern and the values were alternating. So we have tile 2, tile 3, tile 2, tile 3. And this just extends on to infinitum essentially. And let's say we use the same encoding to try to compress this data. What the compressor is going to try to do is count the number of instances of tile 2. It's going to put a counter down of 1 and say, write 1 instance of tile 2. It's going to count tile 3. It's going to go, there's only 1 instance of tile 3, so it's going to put down a counter in tile 3. It's going to do the same thing, 1 instance of tile 2, another instance of tile 3. Now look what this compressor did. It actually doubled our data because there was no consecutive tiles that it could compress. This is a major flaw. So the way to get around that is to put in directives that the decompressor can read and realize, hey, I don't want to be compressing this data. I'm just going to read it as raw data, as is uncompressed. So it's not saving data, but it's preventing it from doubling with this business up here. So what that data would essentially look like is you have compressed data, so we have 08 FF, we have 06, 00, we have 05, 01, this is compressed data. Then it's going to be trying to read a length, but instead we give it a directive. So I would give it the directive FD. You can use FF. I'm using FF for another directive, so in this instance I'm using FD. Just in case this isn't clear, this is the directive here. And then we still give it a length. So the data stream up here is going to be 4 instances of single tiles. So we put down 4. And then we put the uncompressed data. So what this is essentially saying is load 8 into a counter. Write F counter number of times, which is 8. Load 6 into the counter. Load 0 counter number of times, which is 6. Load 5 into a counter. Write 1 5 amount of times. Load FD. It reads FD as a command to say, all right, we're not doing the old song and dance anymore. We're about to have a string of uncompressed data, so we're not doubling anything. The next one is another counter. So we're going to read out 4 bytes of uncompressed data. Then we read 2, we read 3, we read 2, we read 3. And then it's going to expect another length. There's nothing else required because we had a directive and we had a counter. Now it's back to reading counters and data again. So let's say this screen had some sort of repeating image on screen, and this data was repeated for some reason. So we have 8 instances of F, 6 instances of 0 again, 5 instances of 1. That's the basic idea. And overall, with these two things combined, you could compress a lot of data. The only additional thing you need is another directive to exit the routine, or else it's just going to continue to try to fetch a length and try to write the next value to screen or whatever you're using the data for. And my exit directive is FE. I kind of correlate the mnemonic E as exit. So that's exit directive. And that's the basic concept behind the encoding that I've been using. There's some other exceptions in there, but I'm not going to get into it because it's more complicated. And that's the basic idea. Now, to put this all into perspective, it would be helpful to actually look at some level data and see how much this is actually helping. So I have some level data opened up. So over here on the left is a completely uncompressed screen on the NES. It's about 1 kilobytes worth of data. That's an awful lot to be storing just willy-nilly when you're trying to make a game. This, mind you, is one single screen, which with a scrolling level you could have a level that's maybe 10 screens wide, 20 screens wide. And right there, if each screen is 1 kilobyte, that's 20 kilobytes of your 32 kilobyte program, which isn't feasible. You have to start compressing. So next, this little screen right here is the basic run length encoded level data. So this is just the super simple length and tile setup with no exceptions. And look how much we've already saved. It's more than half of the level data is saved. It's probably about 40% by the looks of my particular screen. Now the next one is adding in that exception for not doubling your data if it's alternating patterns and just writing the uncompressed string. So that's what this one is right here. We saved a little bit more. And there's other exceptions you can do. In this particular example, I have a bunch of 1, 2, 1, 2, 1, 2 alternating patterns. I created another directive and another exception to read this as how many times do you write a specific string over and over and over again. So this would be compressed essentially. FC is the directive. Write this E number of times, and so sorry. FC is the directive. The string length is 2. Write this string E number of times, and then the tiles are going to be 02. So something that would be looking like this is going to be 1 instance of the string, 2 instances of the string, 3, 4, 5 would look like this. FC is the directive. The string length is 2. You write these 5 times. The data is 1 and 2. So I've just saved half of this data by using another directive. And there's just multiple ways you can do this sort of thing and compress the data even more. And if I put these side by side, there was the original uncompressed, and this is the compressed data using several different methods, but run length encoding is like the overarching, just kind of the backbone of the compression method. Okay, so what does that actually look like in code? So in your ROM, you're going to have your level stored somewhere, your level data, and that's usually included as a binary. So included binary, reference the actual file, which may be called level 1 or something similar. And the data structure to this is just the normal run length encoding. So we have a length, a tile value, a length, a tile value, length, tile value, and then at some point when it's reading all these lengths, it's checking for an exit directive, so it'll eventually get to that and exit the routine. So what do we need to make this happen? We need a pointer, and we're going to put that on the 0 page of RAM. This it's going to allow us to index into the level data properly. So this is the low byte of pointer, and this is the high byte of the pointer. I don't think we need anything else in terms of variables. We'll add them if we need them. What we have to now do is load that pointer with our level data. So let's call just the main function load level. That's what we're trying to do. So let's load the low byte of the level data and store that into the low byte of the pointer. And then we do the same thing to the high byte. So load the high byte of level data. And we store that into the high byte of the pointer. Now we need to tell the picture processing unit that we want to draw to the screen, and we need to tell it an address at where we want to do so. So in order to do that, we will load the high address, the high byte of the address that we're trying to write to. So the first screen on the NES is at address 2000, so we write 20. So load high byte of screen location address, and we store that at 2006 of the PPU, 2006 of PPU sets write address. Then we load the low byte, which is just 0 if the address is 2000. And we store that again at 2006. Because we're telling the PPU what address we need to be storing at. Okay, so that's properly set up. I should probably clear the high-low latch as well, just in case. And you just read from 2002 to make that happen. And that ensures that this load 20 store 2006, load 0 2006 happens in the right order. Now, I know I'm going to be using Y to index. So what I would normally do is I would load Y with 0 to initialize that value. But we're already using 0 up here to actually store to our PPU. So we can combine those actions. Let's just change this load A to load Y and store A to store Y. And we're going to be hitting two birds with one stone. We're initializing our Y register, and we're loading 0 into 2006. So that's all we need. Now we can actually start fetching. So we can dip into the data using our pointer to actually get the links and get the tiles and write them to the screen. So we'll put in, this is our fetch routine. We will load from our data at index Y, which is 0. And this is our length. Loading length from data. we need to increment our index, which is y, but we can't just do the normal old increment y and continue on, because our data set may very well be more than 256 bytes. And this y register can only hold up to a 256 valued number because it's 8 bits. So we need to deal with the overflow. In order to do that, we want to write a function. And to call a function, we use jump to subroutine to jump to a function and then return afterwards. So let's just call this increment y, because that's what it's going to be doing. Increment y register for indexing. Let's put this function down here. And first we have to increment y, but then we have to check y. So we compare y with 0, and that's checking if it's overflowed. If it has not overflowed, so break if it's not equal, to return. So just return if it's not equal. And that jumps back up to where we called the function and continues the rest of the routine. Otherwise, we have to increment the high byte of our data pointer. So if overflow increment high byte for indexing 256 plus. Okay, we can continue. So we've loaded our length, we've incremented our index, and we want to store that into a counter. We can use the X register for that. We don't have to create a variable. Well, you could store A into a counter. You could put your counter as a variable on RAM, and that could be remembering what the value of your counter is. You can decrement it. You can do math with it. But we have another register open on the CPU that we can just utilize, and I think it's just an easier way, and you're not using as much RAM space. So we transfer the value that's stored in A into the X register in order to use it as counter. So transfer length value to X register for counter. Okay, so next, so we've transferred it over to the counter. Oh, next we just have to load the tile value. So we did back into our data set at the register Y, which is now the second location. So this is going to be load tile value. We again need to increment our index. So we call our subroutine increment Y, increment our index. And now we have a tile value stored in A, and we actually want to write to our screen. And we have our counter stored into X that we can use to then write that multiple times. So in order to do that, we need a loop. So we're going to write loop, and we're going to write that loop function. So store A, which is our tile value, onto the screen using port 2007 of the PPU. Just like we set our screen location on these registers of the PPU 2006, the PPU requires that you write tiles through a port because you don't have direct access to the actual video RAM, so you have to run it through a port, and that's what 2007 does. So store tile values to screen through port 2007. And we decrement our X register because that's our counter and we've just stored something. We compare X with 0 to see if it's finished. Sorry, let me write my notes still. Decrement counter. Compare if 0. And if it's not 0, so break if it's not equal, back up to loop. And keep storing that same tile value that's currently in A, decrementing our index, and just keep looping until we reach 0. And once we have reached 0, we want to jump back up to fetch another length. So loop X amount of times and return to fetch when done. Okay, so this is the main idea behind it all, except there's one specific flaw with this routine that we just wrote. There's no exit parameter, because remember, we have to read that value to exit, or else this is just going to loop infinitely, because it's going to fetch a tile, set it as a counter, loop to write it to the screen, and once we break out of loop, we jump to fetch, which I can't spell for the life of me. So we jump back up to fetch, and it just does that over and over and over. So when we're trying to read another length, i.e. trying to fetch something from our data, we need to try to detect our exit directive. So our exit directive is going to be the value FE. So FE. So once we load a piece of data, let's compare it with the value FE. Break if it is equal to end. And then down here, we can write an exit. Actually, let's call that exit. So break if it's equal to exit. And then we write exit, and we return from subroutine. And that's it. So this is that basic run length encoding. So we added a pointer, we loaded our data address into the pointer, we told the PPU address we wanted to write to screen 1, which is at location 2000. We fetched a length, we compared it with our exit directive. If it's not that, we continue on to the rest of the decoding. We transfer that value to X, which is our counter. We load the tile value, we write that to the screen, decrement our counter, and loop until our counter reaches 0, and continue fetching until we hit our exit directive. And that's a simple way of decoding run length encoding. I'm not going to go over the exceptions in this video, but maybe look out for future videos on all that sort of stuff. Hope you enjoyed. Thanks for watching.